In this video, we'll talk about another way to come up with a solution to an initial value problem. To demonstrate this technique, consider the initial value problem dy dt equals y with initial condition y of 0 equals 2. To be clear, we can solve this differential equation. We could use separation of variables, but we wouldn't even need to do that because we've seen that any differential equation of the form dy dt equals y has solution c times e to the t. But for now, let's assume we don't know how to solve this equation and consider a new technique. So I'm going to assume that a solution to this initial value problem can be written as a power series, and in particular, one centered at 0. We'll come back to why we center it at 0, but we'll see a connection with the initial condition. So for now, let's assume the solution has these unknown coefficients, a sub k. So I've got y equals a sub 0 plus a sub 1t plus a sub 2t squared, etc. And so there are a few things I want to do with this. One of the things we're going to do is rewrite the differential equation in terms of this power series representation. For one, I have that if that is y, then dy dt is just the derivative of the equation I have in pink there. So taking the derivative with respect to t, a sub 0 would go away, a1t would become a1, then we'd get 2a2t squared plus 3a3t cubed plus 4a4, whoops, actually these exponents are wrong. We would get 2a2t to the first power using the power rule, plus 3a3t squared, 4a4t cubed, etc. So this is just term-by-term differentiation, which we've seen we can do with power series. The important step here is that now if this power series is to solve the differential equation dy dt equals y, that means that my blue equation and my pink equation would have to be equal for all t. So dy dt equals y implies, so I'm just going to rewrite these equations, a1 plus 2a2t plus 3a3t squared plus 4a4t cubed, etc. must equal a sub 0 plus a1t plus a2t squared plus a3t cubed plus a4t4, etc. So that's what it means then if this is a solution and it does satisfy that differential equation. So what we're going to do here is now try to find each of the coefficients, a sub 0, a1, a2, etc., and then hopefully devise a pattern so that we can actually figure out what function is associated to that power series. So we'd like to start with a sub 0, and one thing I haven't yet used is the initial condition. So we're going to use that right away. So starting with this, y sub 0 equals 2 is the initial condition. So if we come back to my pink equation for y, plug in 0 for t, notice that the only thing that's going to be left is a sub 0. So plugging in t equals 0 to my solution function yields a sub 0. We need it to equal 2, so that tells me that the coefficient a sub 0 must be 2. So now at this point we've satisfied one of those coefficients. And what I'm going to do to solve the others is what I'm going to classify matching coefficients. So in my equation up here, I'm going to say that these two sides are going to be equal for all t if the constant terms are equal and the t to the first power terms are equal, and so on. So I'm going to match the like coefficients. So when I start, I'm going to take the constant coefficients on each side. So that's going to look at these two. So the constant term on the left is a1, and the constant term on the right is a2. So it must be that a1 is equal, sorry, I said a2, but I meant a sub 0. And at this point, we know a sub 0 is 2. So this tells me if a1 is equal to a sub 0 and a sub 0 is 2, it must be that a1 is 2. So next, I want to go through and look at the coefficient of the t to the first power term. So on this side, it's 2 times a2, and on this side, it's a1. So that gives me the equation 2a2 equals a1. We know that a1 is equal to 2 from our previous step. So this tells me that a2 should be equal to 1. Next, I'm going to take the coefficient of t squared on each side and set those equal. That gives me 3a3 equals a2, or 3a3 then must be equal to 1. So a3 is equal to 1 over 3. If I next go through and equate the coefficient of t cubed on each side, that then gives me the equation 4a4 has to equal a3, which means 4a4 has to equal 1/3, which means that a4 is equal to 1/12. So I want to keep solving for coefficients until I can get to a point where I can establish a pattern. So of course I've kind of exhausted the terms that I've written on the left side, but I know that the t to the fourth power would have coefficient of 5a5 on the left-hand side. And I still have it written on the right-hand side, we would get a4. So 5a5 would be 1/12, meaning that a5 would be 1 over 60. So something that is a useful piece of information here is actually to not simplify too much. And because if I simplify too much, I might overlook a pattern. So my hope is that I can find a pattern so that I can figure out what the general coefficient a sub k would be. So one thing that's starting to be significant is that we have these 2, 3, 4, 5. It's making me think of a factorial, and that makes sense because we were bringing down the powers here. But of course, these numbers aren't quite the same as a factorial. The bottom here is 5 times 4 times 3. This is 4 times 3. Of course, this is just 3. So one thing we could think about is it's like the denominator is missing the 2 that would prevent it from being a factorial. So that would mean then that I could write this as a 5 factorial here if I put a 2 up top to reflect the fact that there's a missing multiplier of 2 in the bottom. And likewise, I could write this one as 4 factorial and put a 2 in the top. And this pattern extends. This is 2 over 2 factorial, 2 over 1 factorial, and remember that 0 factorial is defined to be 2, or 2, it's defined to be 1, so that pattern extends backward. So this process of having to go and look for a pattern, in some sense, I could have avoided that if I didn't simplify pretty much when I got to this step. So I could have written a2 is equal to 2 over 2 and not simplify that to 1, because then when we would get to the next step, we would have 3a3 is equal to 2 over 2, and I would have been able to see that 2 divided by 3 factorial. So in general, if you are working through a problem where we're trying to assume series solutions, it's often a good idea to think about not simplifying so that you have a better chance of noticing a pattern. However, at some point when I get to the realization that it looks like my coefficients are 2 over k factorial. So let's think about what this means. I started with the assumption that my solution is this power series. And of course, I could put that power series into sigma notation if I wrote it as a sub k t to the k for my terms and sum from k equals 0 to infinity. What we just found is a formula for a sub k. We said that was 2 over k factorial. So given that, let me get another sheet here. So we found that formula. Then this means that our solution y is, we said, the sum of a sub k t to the k. And we just found a sub k to be 2 over k factorial. So what we'd like to be able to do is look at this series and now think, is that the Taylor series centered at 0 for some function that I know? And so we think about the Taylor series we've seen, and notice that I could rewrite this as the sum from k equals 0 to infinity of 2 times t to the k over k factorial. And I could bring that 2 out front. And the reason that that's helpful is that this should look familiar. This is the Taylor series centered at 0 for e to the t. So we get that our solution is 2e to the t. So if I had used separation of variables to solve this differential equation, I would have gotten exactly the same solution. I also talked about recognizing that it should be something of the form c e to the t, and that constant c would be determined by our initial condition. So this matches what we would have found otherwise. Now, the other thing to consider is, of course, on this example, I would not want to use this technique. I would rather use either of the other two ways we discussed of solving this because of efficiency. However, we've seen that separation of variables, of course, can only be used when we have a separable differential equation. This technique does not require that. So we're going to see examples of things that, with what we've seen so far, we wouldn't know how to solve other than using this technique. The nice thing about starting off with this example is that because we can find the solution in another way, we at least have verification that we ended up with the correct answer. So now that we think about that, I want to go back to our original assumption that we started with our series being centered at 0. And we'll see that all of the examples we encounter in this class, we will really start with that assumption. But what that comes from is really this part. So notice that by assuming that our power series was centered at 0, when we plugged in the initial condition, y of 0 equals 2, that allowed us to immediately find a sub 0. So by making that assumption about how to represent the power series, it just so happened that our initial condition became immediately useful. If instead we had started with maybe the assumption that it was, let's say, centered at 1, then my polynomial would have been a sub 0 plus a1 times t minus 1 plus and so on. And basically all of these t's would have been t minus 1s. And the problem with that is that if you plug in 0 for t, you would not have gotten just a sub 0. You would have gotten an infinite sum. 0 minus 1, each of those t's would be negative 1. So we're starting off and trying to make an assumption about how we're going to represent the series. I chose to center it at 0 because that's going to be the way that I'll be able to take advantage of that initial condition to immediately find one of those coefficients.